Today, we are diving deep into one of the most powerful tools out there for researchers, structural equation modeling. Now, I know it sounds kind of heavy, but stick with me because this is all about how we answer some of the biggest and most fascinating questions in science. So think about this for a second. How would you actually measure something like motivation? I mean, you can't just whip out a ruler or a thermometer for it, right? Instead, you have to look at clues, things like how often a student studies or their answers on a survey. But then, how do you connect those concrete bits of data to that big, fuzzy idea? And even more important, how do you test if motivation is actually causing a change in another big idea, like achievement? This is a massive puzzle for researchers.
And look, this isn't just some obscure problem for a handful of scientists. This is a fundamental challenge in psychology, in economics, you name it. We're always trying to figure out how these huge, complex concepts are all connected.
Your basic statistics, they're great for looking at one or two things at a time. But a real scientific theory, it's a whole web of ideas all linked together. Trying to test that whole web one string at a time is like trying to understand how a car works by only looking at one spark plug. You're going to miss the entire engine. Okay, so this right here is the absolute core of the whole thing. On one hand, you've got observed variables. These are the things we can actually count and measure. Test scores, answers to a survey question. But on the other hand, you have latent variables. These are the big abstract ideas we actually care about, like intelligence or well-being. The entire game is about using what we can see to understand what we can't. So, how in the world do we bridge that gap? How do we take our big ideas about the unseeable world and actually test them like a real science? Well, that is where the star of our show today comes in. And that's where structural equation modeling, or just SEM, makes its entrance. It's this super powerful statistical framework that basically takes methods you might already know, like regression and factor analysis, and smashes them together to create something much, much bigger. It's built from the ground up to test those big, messy, interconnected theories. And here's a great way to think about it. Imagine a researcher is like an architect. Before a single brick gets laid for a new building, the architect draws up a detailed blueprint of how everything is supposed to connect. That's exactly what SEM lets a researcher do with their theory. They get to draw a complete blueprint of all their ideas and how they're connected before they even touch the data. Now, this blueprint drawing stage, it has a formal name. It's called model specification. And it's where you turn your theory from words into a precise diagram. You gotta know, this is not just some warm-up exercise. As the expert Rex Kline puts it, this is the most important step. Why? Because if your blueprint is wrong, it doesn't matter how great your data is, the whole building is gonna be unstable. The whole SEM journey kind of boils down to four main stages. First, you specify the model. That's drawing the blueprint. Then you have to do an identification check to make sure the math can actually be solved. After that, you bring in the data for the estimation phase, where you figure out how strong all those connections in your blueprint are. And finally, you assess the fit, which is the moment of truth, where you see if your grand theory actually holds up. Okay, so you've drawn your blueprint, you've crunched the numbers, but the huge question is still hanging in the air. Does your beautiful theory actually match up with reality? And that brings us to this crucial idea of model fit. Let's use another analogy here. Think of your theory as a custom-made suit, and your data is the person you made it for. Assessing model fit is like having the customer try on the suit. Does it actually fit them, or are there parts that are too tight, too loose? Is it a perfect match, or does it just not work? Now, this fitting process happens on two levels. First, you've got the global fit. That's the view from 10 feet away. Does the suit overall look pretty good on the person? That's what a big picture statistic tells us. But that's not enough. You also need to check the local fit. This is where the tailor gets right up close, checking for specific spots where the fabric pinches or bulges. A really good model has to pass both of these tests. It has to look good from a distance and up close. And there's a really important philosophy here, summed up perfectly by the statistician George Box. The goal isn't to build some ridiculously complicated model that explains every tiny little weirdness in your data. The goal is to find the simplest, most elegant model that still does a great job. It's about parsimony. Sometimes the most powerful insights come from keeping things simple. All right, so how do we actually do all this? Well, it really comes down to two killer techniques that give SEM its dual power. First, for making sure your measurements are solid, and then for actually testing your causal theories. First up is Confirmatory Factor Analysis, or CFA. Think of this as building the foundation of your house. Before you can test your big theory about motivation and achievement, you have to be sure that your survey questions about motivation are all actually measuring the same thing. CFA is the tool that checks that for you. It's how you make sure your ruler is actually measuring inches. So once your foundation is solid, then you move on to structural regression models. This is where you get to test the really exciting stuff, the causal pathways of your theory. We're not just saying motivation and achievement are vaguely related anymore. Nope, we are now testing the idea that motivation causes a change in achievement. You can even use powerful frameworks like Judea pearls to make all your causal assumptions crystal clear and testable. So that's the elegant 1-2 punch of SEM. But that's not all. You know, real-world data is always messy. Sometimes people don't finish a study, leaving you with missing data. SEM has amazing tools like multiple imputation to handle that. And what if you want to study how something changes over time? Well, there are latent growth models for that, which let you track things like how a kid's reading skills grow from first grade to fifth grade. It's incredibly versatile.
But, and this is a really big but, with all of this amazing power comes a huge responsibility. And there's one critical, kind of sobering fact that every single person who uses SEM has to face. It's the problem of so-called equivalent models. And what this means is that there could be a totally different model out there, with arrows pointing in different directions, making completely different causal claims that explains your data exactly as well as your favorite theory does. The stats, the fit numbers, they can be literally identical. And this is a massive challenge. It's a wake-up call that guards against confirmation bias. You know, it's so easy to find a model that fits your data well and just declare victory. But a truly good scientist has to stop and ask, are there any other explanations that could fit this data just as well? Ignoring that question is a huge mistake. A good fit doesn't prove your theory is the one and only truth. Which leaves us with this final, really important question. If the numbers alone can't tell you which of two theories is right, then what can? Well, the answer isn't in the statistics. It's in having a stronger theory to begin with, better study designs, and more data over time. SEM is an unbelievably powerful tool for testing a theory, but it's no substitute for the hard work and critical thinking that it takes to come up with a great theory in the first place.